Hello and welcome to another session, and today we will talk about some other converter topologies of multi-level converters. Now, there are hundreds of converter topologies for multi-level converters, and it is impossible to summarize them in such a small lecture, but what I thought is to include in this other converter topologies is to introduce you to 2 or 3 topologies and then some other cell structure for MMC. So, this was the main idea behind having this subject of topologies. Of course, what we will cover here are basically one topology that is called the flying capacitor converter. We will cover that. Then we will cover alternate arm converter, which is a variant of MMC, and the third one that we will cover are different cell structures. I mean, in MMC we know, or MMC or CHB we know that there are half bridge or full bridge cells. So, the third part will be like what are the variants in these cells. So, basically we are covering 3 topics here. First, the flying capacitor, second the alternate arm converter, and third different cell topologies for MMC. So, let us see what is the first one. This is the flying capacitor converter, in short FC converter or FCC. Okay. This converter was one of the older multi-level converter topology, which was commercially implemented by one manufacturer. That is why I have included it in this subject or in this lecture session. However, if you when you fully understand this converter, you will see that there are some drawbacks for this converter, for which it has not gained a lot of momentum. However, the concept is interesting and we should know the concept, because based on this concept it is possible to have other variants, or we can include it along with some other conventional topologies. So, what is there here in this converter? So, if you see here in this topology, what do we find? Basically, the word flying capacitor means in this converter there are a number of capacitors, okay, and there is one DC source. There may be several capacitors, and these capacitors can be connected either in series or they can be bypassed. Okay. So, let us understand the operation by seeing one capacitor which is connected to the DC source here. Okay. So, this side is DC source. I mean, ideally we should have this is a DC source. So, it is like this. Okay. It is not capacitor, this is DC source. Okay. So, this side is the DC source and this is the capacitor. So, how are we going to operate? So, you can see here that this DC source is connected to the capacitor via these switches here. Okay. So, basically what are we doing here is that we can insert this capacitor either in series with this DC source or we can bypass the capacitor. For example, suppose I want to get I want to see this voltage AO VAO. So, if I turn on switches S3 and S4 here, then what will happen is that this VAO voltage will be 0. Okay. This voltage will be 0 if I turn on the lower two switches. Now, suppose this DC source is having a voltage of VDC and this capacitor is charged to VDC by 2, that is half of this DC link. Then we can suppose I want to get VDC by 2 in VAO, then what can I do? I can turn on these two diagonal switches. Then what will happen is, so starting from here I go like this and like this here. So, VAO voltage will be equal to the capacitor voltage once I turn on S2 and S4, and the capacitor voltage suppose we maintain it at VDC by 2. There is also one other path by which we can realize VDC by 2, and that is going from here through S1 through S3 and getting like here. This is also possible, you can see here, this is also possible. So, by turning on S1 and S3 or turning on S2 and S4, we can get VDC by 2 voltage available between A and O point. Of course, the last option is to turn on S1 and S2 and then we get VDC voltage here. So, you can see that this capacitor is sometimes getting bypassed and sometimes connected in series to the DC source. Okay. So, by this method we are getting this 3 levels of voltages between A and O, and so this will produce 3 levels of output voltage. Now, you can easily understand that this capacitor is not a stiff source. So, therefore, it will, when the current is flowing through the capacitor, it will either charge up or it will discharge. So, therefore, we must, in order to keep the voltage at VDC by 2, we must maintain the voltage on the capacitor in an average sense. So, we should, if the current is flowing for certain duration, we will charge up the capacitor, and for certain duration we will discharge the capacitor, and this will be possible by using this state here. Only is in this state the capacitor, that is the VDC2 state, VDC by 2 state, the capacitor can be charged or discharged, whereas in 0 and VDC state the capacitor has no effect, the voltage on the capacitor has no effect. So, therefore, we have to apply these two voltage states by using the two multiplicities, okay, and thereby it is possible to maintain the capacitor voltage. We have to go on doing this all the time, so as to keep the capacitor voltage at VDC by 2. You also note that these two switches must be operated in a complementary fashion, otherwise you are going to short circuit. And we also note that the rating, the voltage rating of all these switches here is equal to VDC by 2. Okay. All the rating is equal to VDC by 2. The current rating is equal to the load current. Okay. Now, having understood this very simple circuit, you can then add more number of capacitors to get more number of levels. So, for example, you can have this as VDC here, and then you can have one switch here. Now, I am drawing a generic switch. Okay. So, you can have one set of capacitor here, and then you can have another set of capacitor here, and like this. Okay. So, in this case, by using different combinations of these switches, you can allow the current to flow this way, or you can allow the current to flow this way. Okay. So, yeah. So, therefore, in a similar way, for this capacitor you can allow the current to flow this way, or you can allow the current to flow this way here. So, now you can see that using these combination of switches, we can charge or discharge the voltage or charge or discharge the capacitor. Okay. And you can have several such stages. One advantage of this topology is that you have a single DC link, and you are creating more number of levels by introducing these capacitors. So, it was commercially implemented by one manufacturer. However, there is a drawback, and as you can understand here, that the load current is always flowing through these capacitors, right. The load current is always flowing through these capacitors. So, in case of a multi-level converters, we know that the load current can be quite high. As a result, these capacitors must be big in size, otherwise because of the high magnitude of the load current, they will quickly charge or discharge, and their voltages will quickly change from the nominal value. If the voltages change from the nominal value, then we do not get the multi-level waveform which we desire. So, therefore, in this topology, bigger size of capacitors must be placed. The other way, if you want to keep a small size capacitor, then what is the other way is that frequent switching has to be done. So, you are continuously charging or discharging the capacitors. So, the switching frequency of these switches increases. So, that is the compromise. Either you put a bigger capacitor or you increase the switching frequency and hence switching losses in this converter. However, the idea is sometimes used in other types of converters. For example, flying capacitor can be the flying capacitor topology can be integrated with NPC, so as to get more number of levels like that. So, this is what about the flying capacitor converter. The next topology that we will see is the alternate arm converter. Okay. Now, what is the alternate arm converter? Alternate arm converter has been proposed more recently after MMC has been proposed, and this is a variant or is a hybrid topology between MMC and a 2 level converter. As you can see here, this topology is having a very similar structure like MMC. You can see there are a lot of cells and there is a arm inductance. However, there is a additional component here which is called the director switch here. In this figure we have shown the director switch to be a single IGBT, but in practice it is basically a series connection of several IGBTs. So, this is the key feature of an alternate arm converter, which is this director switch. The function of the director switch is to connect or disconnect the arms. So, with the help of this director switch, you can either connect this arm or you can disconnect the arm. So, basically the converter is operated in such a way so that only one arm is operating in one half cycle of the AC waveform. In the other half, the director switch is opened and this arm is completely removed from the circuit. Okay. I will explain it a little bit in more details, but what you can think of is that this director switch is nothing but a switch here. Okay. This is a switch here. So, during the positive half of the AC waveform, that is the positive half of this AC waveform, we will use this upper director switch and we will open this switch here. In the negative half of the AC waveform, we will use this director switch and will open this one. So, the one arm is only used in one half of the AC cycle. So, therefore, it is claimed that this topology will give us lesser loss as compared to the conventional MMC. We will discuss it a little bit in details after a few minutes. The submodules here are usually made up of full bridges. Okay. So, that is what I have just told. The upper arm produces positive half cycle and lower arm produces the lower half cycle of the AC waveform. So, each cell in the arms should be rated for half of the DC link voltage. Rather, I will say not each cell, each arm should be rated for half the DC link voltage. Okay. So, let us see how this happens. What we can see here is we can draw the equivalent circuit of alternate arm converter, which is very similar to the conventional MMC. We are not drawing the arm inductors, we are neglecting the drop across the arm inductor. So, here is the director switch D1 and D2, and we also have this as VAU and this as VAL, and we have E by 2 here and E by 2 here, and this is the VAN voltage, the AC voltage. Okay. So, we can understand the operation of the converter. So, as I told you, D1 and D2 are complementary. It is not exactly complementary, there is an overlap time period, but let us first understand that suppose let us assume that D1 and D2 are complementary. So, when D1 is on, okay, what will be the equation? If I write the KVL here, so then VAN plus VAU minus E by 2 is equal to 0, and during this point of time D2 is off. So, this side is off, this switch is off. Now, next portion D2 is on, next half cycle. Okay. This is the positive half cycle of the AC waveform, and this is at the negative half cycle of the AC waveform. Okay. And during this time D2 is on, and so the equation is VAN minus VAL plus E by 2 is equal to 0. Okay. So, I can give it as number 1 and number 2 equation. So, therefore, I can write from 1 VAU is equal to E by 2 minus VAN, and VAL is equal to E by 2 plus VAN, right. So, let us then draw the waveforms. Okay. So, let us first draw VAN, and this is the VAN waveform, and let us assume that this is spanning between E by 2 and minus E by 2. Okay. So, therefore, what is how should we draw VAU voltage? So, if you see here VAU voltage, this is omega t. If you draw VAU voltage, as you can see VAU voltage during the point, the positive half cycle of the AC waveform, that is during this time. So, there are 2 half cycles. So, during the positive half cycle it is E by 2 minus VAN. So, therefore, if this is E by 2, therefore, this waveform is E by 2 minus Vn. So, it is like this, and then the VAU voltage, and then D1 goes off. So, D1 is on here and D2 is on here. So, therefore, during the first half cycle VAU voltage is like this, and in the second half cycle it is completely out of the circuit, and so VAU voltage becomes flat like this. Okay. So, this is the waveform of VAU, and you can clearly see that the rating of VAU is equal to E by 2. You can see here the rating of VAU is equal to E by 2, which is half that of conventional MMC. Remember, in conventional MMC we had said that the voltage rating of the arm is equal to the total DC link voltage. Here the voltage rating of the arm is half the total DC link voltage. Okay. Now, looking into this equation once more, we can also say that the rating of VAU is because in the positive half cycle. So, in the positive half cycle, so since in positive half cycle 0 less than equal to VAN less than equal to E by 2. So, therefore, we can say that 0 less than equal to V by U less than equal to E by 2, this you can say. Okay. So, therefore, this statement is valid. What is the voltage rating of the directed switch D1? So, voltage rating of D1, how much is it? The voltage rating of the directed switch D1 can be obtained when D1 is off and D2 is on. Okay. So, the voltage rating of D1 can be seen, suppose you write it like this. So, therefore, VAN minus VD1 minus VAU plus VAU minus E by 2 is equal to 0. Therefore, VD1 is equal to E by 2 minus VAU minus VAN. Okay. Sorry, no, there is a mistake. So, therefore, VD1 is equal to minus E by 2 plus VAU plus VAN, because you see here during the negative half, that is during this time, the VAU voltage is clamped to E by 2. So, we can say since VAU is equal to E by 2, okay, therefore, the voltage is of this one is equal to VAN. Okay. So, this means that the voltage rating of directed switch is equal to the peak AC voltage. Okay. So, therefore, voltage across D1. So, if I plot the voltage across D1 here, the voltage across D1 will be equal to 0 in the positive half, because it is conducting. So, this voltage will be equal to 0 here, and the voltage is equal to VAN when it is off. So, therefore, this will be equal to VAN. So, this is follows VAN voltage here. Okay. So, this is what appears across the directed switch D1, and accordingly we have to design it. The last part you can also similarly draw VAL. I am not deriving it, but VAL also has a voltage like this. Which is, this is E by 2 and this is V. So, VAL voltage is something like this. Okay. So, this gives you a basic understanding of alternate arm converter. Now, this cells, so it is also to be noted that AC voltage in the converter may not be less than E by 2. That AC voltage even can be more than E by 2, and so full bridge modules or sub modules can be used. And because of this full bridge modules, we have seen earlier that inherent fault tolerant capability of the converter can be provided. One thing that we should observe here, that okay, fine, this converter, the arm voltages are half the DC bus, arm voltage rating is half the DC bus, that is a very attractive feature. But then what about the capacitor balancing? Okay. These cells are all made up of capacitors, and we should have a similar strategy, okay, like MMC, in order to keep the energy balance. Now, so for this to happen, there is, in the operation of the converter, there is a small overlap time period, and in this overlap time period both these switches are turned on, both the director switches are turned on. When they are turned on, it is as if like there is a short circuit, and a current will flow through this path, through the DC link and through both the arms, and a DC current, this is the DC current that will flow, and this current makes sure that the capacitors are again charged back, so that they can work in the subsequent AC half cycle. Remember, like in MMC, active current is flowing through the capacitors in the arms, and so it will lose energy, and somewhere in your cycle, somewhere in the full cycle, you have to replenish this charge of the capacitors, and this time is this overlap time. During the overlap time, these two switches, for a brief period of time, they are turned on, and so the DC will flow through this whole arm and will replenish the capacitor. So, this is an alternate strategy. Okay. This is an alternate strategy as compared to MMC. In MMC, the DC circulating current or the DC current was flowing continuously, and that is why we always had these two cells. The DC was flowing continuously. However, in this case, what we have done, we are not allowing the DC to flow continuously, rather for a short period of time, maybe during the end of the half cycle and the beginning of the half cycle, a short period there, we will short or we will turn on both the director switches and the current will flow. This will make sure that the capacitors are properly charged up. So, the losses in this converter because are lower, because one arm is conducting at a time and a half cycle. So, in one half cycle this arm is conducting, and in the other half cycle this arm is conducting. So, you can see in the web there are many publications now coming up with alternate arm converter. I just wanted to introduce you to this topology. Next part, as I told you, there are 3 parts of this lecture. We covered the flying capacitor, we covered the alternate arm converter, and now we will cover what are the different types of submodules proposed for MMC. Okay. Now, half bridge is the most economical and the easy to implement and the simplest topology, half bridge based MMC. But half bridge based MMC has a serious drawback, and that is that during fault condition, that once we have turned off the IGBTs, it is a totally uncontrolled, it works totally like an uncontrolled rectifier. The diodes are on and the fault current will flow, you cannot stop it. Okay. So, people have come up with other types of submodules. Okay. The main idea here is to limit the fault current along with some additional beneficial features. We will see 3 or 4 of them now. So, for example, this is one such thing, clamped single submodule. Okay. So, you can see here that in this topology we have this half bridge here along with additional switch and diodes here. They are all rated for half the DC voltage. Okay. Now, when the normal during normal operating condition, this switch S3, this is always turned on. Okay. So, this point is connected to here, and so there is absolutely like a half bridge operation of this converter. Now, when there is a fault, note that this current will flow here, so that this diode is reverse biased, okay, because this point potential is half VDC and this is 0. So, this is reverse biased. But what happens at fault condition? So, at fault condition what happens is we will shut off these IGBTs here. Okay. If the fault current is greater than 0, that means the current is flowing like this, then how will the current flow? The current will take a path through like this, it will, so this the current is flowing out like this, so it will go in like this here, it will go like through this D4, through this capacitor D2 and like that, it will go out. Okay. You see during in the path of the fault current, this capacitor is present. Okay. If the current I is less than 0, that means this is the current flowing and we have shut off all the IGBTs, then the current will flow like this. It will go like this, go through like this, come like this, go like this and like this here. Okay. Like here through D1, through the whole DC link, through D3 and go like this here if I is less than 0. So, we see that in this topology during the fault condition there is always these capacitors which are coming in the path of the fault current. This is also the strategy that we had adopted when we used full bridge during the operation of conventional MMC. What was the advantage of a full bridge as compared to half bridge MMC? What happened there in half bridge MMC? As soon as we shut off the IGBTs, there was only diode in the path, there was no capacitor. Whereas in a full bridge, if we if we shut off the IGBTs, even then when the diodes are conducting, there is always a path through on which there is the capacitor present. And why is the capacitor important? This capacitor has already a voltage, and that voltage will, or the capacitor rather I will say that the capacitor acts in the path of the rising current, rising fault current, and so the voltage of the capacitor acts like a back EMF, or it will oppose the rate of rise of the fault current. So, the fault current tries to increase, but you have put a capacitor in between. So, it will see a big impedance, this capacitor, and it will first charge up the capacitor. So, the energy of that fault is somewhat getting absorbed in the capacitor in the form of half CV square. So, this is the advantage of suddenly inserting the capacitor in the circuit. So, the capacitor voltage will increase, and it is as if like it is kind of like restricting the rate of rise of the fault current. So, here also in this topology we see the same effect, where during the fault condition, even if only the diodes are conducting, the capacitors are getting inserted in the circuit. So, this is not only true for this topology, but all the next topologies. So, let us see the next one. So, this is the clamped double sub module. Okay. This topology was proposed for DC fault tolerant capacity, but it has a reduced loss as compared to the edge bridge. Okay. So, how does it operate? Basically, you can see here, this is, there are two half bridges. Okay. There are two half bridges here, and these two half bridges work in series. Okay. By turning on this S5 or D5, when this switch is fully turned on here, they are working in series with each other. Okay. So, it is like this, this is the path of the current, for example. Now, when fault happens, right, when fault happens, if this current I is greater than 0, then we have turned off these switches, all these transistors have been turned off. So, you can see that the current will have now two paths. So, one path is like this, current comes here, I is greater than 0. So, current comes here through D1, through D7, through this capacitor, through D4 and goes out. This is one path of the current. The other path of the current is through this D1, through this capacitor, through D6, D4 and goes out. Okay. So, again you see that the capacitor is coming in the picture and it will restrict the fault current. Okay. If I is less than 0, you will see that D3, D5 and D2 will conduct. So, let us see, if I is less than 0, go through D3, through this capacitor, through D5 and through this capacitor D2 and goes through 0. Okay. Again, there is also another sub module. So, there are, I will explain one or two more, like unipolar voltage full bridge sub module. Okay. So, this is like normal condition, this is a half bridge kind of thing, this switch is always turned on. Okay. And S1 and S2 is working with a half bridge configuration. Okay. Now, when there is a DC slide fault, then these switches are opened. So, these are turned off, and if I is greater than 0, so you will see I is greater than 0. So, this diode will conduct and this capacitor will conduct and D4, this is how it will form. So, again the capacitors have come. So, all these sub modules have some advantages. So, all these have the same functionality like the full bridge, but you can see here in this topology, one switch has been reduced. Okay. This switch here as compared to the full bridge, it has been removed. Again, there is one more here. This is also interesting because this will give a 5 level cross connected sub module. So, this voltage here will become 5 level. How can it become 5 level? You can make it like this is Vc and this is Vc. So, this is Vc and this is also Vc. So, therefore, you can see here you can get 2 Vc, Vc 0, minus Vc and minus 2 Vc between these two levels, these 2 points. So, how can you get 2 Vc? Say here comes here, this is plus Vc and another plus Vc. So, if you go like this here, like minus Vc minus 2 Vc goes out like here, sorry, and you can have Vc only. How can you get a Vc? Suppose this voltage is here, it goes like this, Vc goes like this and goes out like this here. So, you can get Vc. How can you get 0? If you get this, then you got go Vc and this you go here and then you directly go out here. bypassing the 2 capacitors. So, you can get 0. Okay. So, in this way you can get 5 levels of voltages from 2 half bridges connected in this fashion. Again, if you see that during fault condition the capacitors will come into picture. Okay. So, a mixture of half bridge cells and 5 level cross connected modules have been reported, but again the losses are more here. So, what I want to say here is that there are different types of submodules also possible. It is not like that only half bridge or full bridge submodules can be used in MMC, but as of now commercially only half bridge or full bridge have been used. These are all kind of like in the research stage. Okay. At least I have not seen like this kind of a submodule being used in a commercial application, but maybe in a future this will, some of them may be used. We saw 3 different structures. One was the flying capacitor. It is kind of like capacitors connected in series or bypassed. We also saw the alternate arm converter, which is a modified or a hybrid version of a 2 level converter and an MMC, and we saw some different types of submodules. Okay. So, many of these, so although FC is commercially implemented, but some of these can be used in for commercial application maybe in near future. Okay. So, with this we end the technical content of this course.